Hi, welcome to the unit about mechanics. We're going to talk about force and motion. That's what mechanics is all about, how forces make objects move. Most famous example, of course, is this ball. If I toss it up, I'm exerting a force and making it move in the vertical direction, and after a while the force of gravity is pulling it back down. So this is all what mechanics is. It's the study of how forces from my hand or from gravity can cause objects to move. What do we mean by move? Well, if the ball would just be staying at one point in space, it would be a rather boring study. Right? So moving means moving through space, right? Which means that your position is going to change. The rate at which your position changes is known as the velocity. Right? So if I plot the position as a function of time, I have some graph, and the velocity is how quickly this changes. And mathematically speaking, that's the derivative of the position. Now, if I know not the position, but I've measured the velocity of the ball, and I want to know where it is, I can also go back and do the inverse operation of differentiating. I have to integrate the velocity to know where the ball ends up. The laws of mechanics were first discovered by Isaac Newton centuries ago. And he formulated 3 laws that we're going to use in this unit and the next to describe the motion of the ball and other objects. The first law simply states that if there's no force, the velocity of the object will stay the same. Simplest example is if the object is standing still and there's no force, it won't be moving. But also if it's moving at a constant velocity, as long as there's no force, the ball will retain its constant velocity. The second law tells us what happens if there is a force. Right? And that says that if there is a force acting on the object will experience a change in the velocity. And the larger the force, the larger the change in velocity. Right? So if I exert a larger force on the ball, it will fly up faster and higher. So to quantify this, we need to quantify changes in velocity. Well, we just saw that velocity was changes in position, right? The time derivative of position. Now the change in the velocity itself is known as the acceleration. And it works in exactly the same way. The acceleration is the time derivative of the velocity. So if we know the force, we know the acceleration, and we can find the velocity by integrating, and then the position by integrating again. Right? And this gives us Newton's second law in its most well-known form. F is m times a. The force equals the mass of the object times the acceleration. So what does that mean for our ball? Well, first, let's look at the simplest case. Right? If there is no force acting on the ball, Newton's first law tells us that its velocity will remain constant. Right? So we have a very simple equation. Velocity is constant. If we want to know the position, you have to integrate the velocity. Right? And well, we want to know the change in position. We start at some point, which we call t is 0, and then we want to know the position as a function of time. Right? So this is the integral of 0 to t over the velocity. You have to be a little bit careful because the velocity itself may be a function of time also, and it's a different t, so this is why I called it tau, the Greek t. Now, the integration of a constant is not very difficult. That's the constant times the variable. That gives us v times t plus some constant, some integration constant. And we can find this integration constant by looking where the ball is at time 0. Right? So the displacement of the ball is simply where it was at time 0. So where it is now minus where it was at time 0. And for the motion without a force, it's simply the velocity times time. All right, that was an almost trivial example. Let's make it slightly more interesting. Right? Let's go to the second law and have a force acting on the ball. Now the velocity is no longer constant, but the acceleration is. If there's a constant force, we have a constant acceleration. And so we can find the velocity by integrating the acceleration. That's the same integral, just the symbols changed, right? So the solution is also the same. The velocity is then the acceleration times time plus whatever the velocity was at time 0. And if we want to get the position, then we have to integrate this again, right? So now we're integrating a linear function, and what we get is a quadratic function. So for a constant force, we're going to get a constant acceleration, and what we're going to get for the position is a quadratic function in time. Right? So there's the quadratic term in time, there's a linear term in the velocity, right? And the constant term which gives us the starting position. Specifically, if we start with zero velocity and at 0 positions, let's put the origin in my hand, right? Then the displacement is simply going to be a half AT squared. To make this concrete, gravity locally close to Earth is exerting a constant force. It's on this ball. It's simply the mass of the ball times the gravitational acceleration, which for planet Earth is about 9.8 meters per second squared. So if I drop the ball, what will happen is that it will accelerate, usually downwards because gravity points down, with this constant acceleration, and its position will be quadratically dependent on time. All right, now that's a bit of a boring movement still. Wait, can we make it more interesting? Well, the standard example that people use here is firing cannonballs. So what happens there? Well, if you fire the cannonball right straight up, like in this picture from Jules Verne, Voyage to the Moon, then only gravity is acting on it. And it's the same as me tossing up the ball. That's already described by this equation we had. I just give it a non-zero velocity at time 0, right? So the second term, the linear term, also comes into the equation. But if I throw the ball a little bit to the side, the motion gets a little bit more interesting. Right? Because now I have a motion in the x direction and a motion in the y direction. In the x direction, there's no force acting on the ball. Right? So we immediately know the solution that came from Newton's first law. In the y direction, gravity is acting on the ball and it's pointing downwards, hence the minus in front of the quadratic term. Now, if we fire from the origin, and we just simply put the origin there at some speed v, what's going to be the trajectory? Well, if I fire at some angle, let's say theta with the horizontal, right? The x component is going to be the cosine of, is going to come from the cosine of the angle, and the y component is going to come from the sine of the angle. Right? So I simply plug this into the equations we have, and we get the equations that you see here. Now that gives us a parametric description, right? As a function of time, we can now calculate what the position is in both x and y. But typically we want to know the actual trajectory in space. We want y as a function of x. Now here, this is not so hard to figure out because we can simply invert the equation for the position x. Right? We can rewrite this equation saying that, well, if x is v times cos theta times t, then I also know that t is x divided by v times cos theta. And now I can plug this back in, the equation for y. And it gives me the y position as a function of the x position. The first term becomes very easy. It's simply the tangent of the angle times the x position. The second term is going to be some constant times the x position squared. So the trajectory of a cannonball or this ball or anything that you throw under some angle is going to be a parabola. Looking like this. And how far your ball gets depends not only on how fast you shoot it, but also under which angle you shoot it. Which is nicely illustrated not just by cannonballs, but essentially anything that's shot up, including water, molecules, airplanes, anything that's being fired away will follow this quadratic trajectory. All right, so that's what happens if you have a single force, or no force at all. But what happens when you have more than one force? That's what we're going to discuss in the second unit.